We're quite lucky today to have Bob Sieck talk to us about launch operations. Bob joined NASA early in his career after a spell with the Air Force. This was in the early 60s, and he worked on pre-launch checkout and servicing of Gemini and Apollo, then went into the Shuttle program. He worked on ground operations for the approach and landing tests. We'll hear more about that testing when Gordon Fullerton comes here at the beginning of December. And then he worked as launch director for a lot of the early shuttle missions, including my first flight, and then went to be the shuttle operations director at Kennedy Space Center. But then after the Challenger accident, he came back and worked on another, 40 or so launches. So with the exception, I think my last launch was in '96. You had already graduated, right? But Bob was the launch director of the first four of my flights, and so he's the head of the whole team of really thousands of people who are responsible for getting the shuttle ready to fly and for certifying that in fact it is ready to fly. And it's a very complicated, critical, and from a safety point of view, absolutely one of the most important things that we do is to figure out when this incredibly complex vehicle is really ready to go. So Bob's going to talk to us both about some of the aspects, the technical aspects of the launch operations, but also I hope that, from a systems engineering point of view, we'll have a chance towards the end to talk about some of the planning that was going on while the shuttle was being designed and some of the compromises which had to be made, some of which we've already addressed, between the efficiency of turning around and maintaining a vehicle like the shuttle vis-a-vis the actual initial upfront cost of it. So with that as an introduction, Bob, I'll turn it over to you.
Thanks, Jeff, and good morning. As Jeff indicated, I got into the business of launching people and payloads into space a long time ago. I was privileged to be part of all of the human space flight programs, so I did a lot of that. What I didn't do, I saw most of, and I have an opinion on all of it. So please ask questions. If I don't have the answer, I'm sure to have an opinion. I'm going to spend a little bit of time. We talk about launch operations, but that's the final 3 to 4 days of a campaign that begins 3 to 4 months before you actually start the countdown clocks and put the astronauts in the vehicle and go fly. So I'm going to spend some time on the background of preparing the shuttle, the ground systems, the flight systems prior to the launch count process, particularly to talk about the engineering involvement and the responsibilities in those processes. But in order to talk about launching, I have to talk some about the operations of putting the final pieces together and doing the tests and inspection prior to launch. And then when I want to get into the real meat of it, which is the human factors, the role of the engineer, the role of the managers in the process of testing, inspecting, checking the flight systems, the ground systems, and certifying that it's okay to put the crew in and go fly. And that's where we're going to spend most of our time. But I got to go through some background first. I don't know how many of you have been to the Kennedy Space Center. Anybody been down to? Okay, so you've seen it's a city where we launch. We've launched everything since the beginning programs: Mercury, Gemini, Apollo. The most prominent fixture is this vehicle assembly building, which was used in the Apollo program to put together the 300-foot tall Saturn Apollo rocket. Shuttle is about half that size, but we use this building to do the assembly, and I'll talk a little bit about that later. But it's a city. We have our own power systems. We have facilities to check out the orbiters, to process the solid rocket motors. We have administrative homes for the people, and of course we have the highly visible launch pads that are out on the ocean. And we also have a runway. When the weather cooperates and we can bring the shuttles back to Florida, we can take care of the landing and recovery there. The process. Talk a little bit about the process. When an orbiter returns from its previous mission, it goes through essentially a disassembly, inspection, and then build it back up and test it to make sure that it's still within the certification base that the engineers set up for it, that you've already heard from previous to this lecture. You would like to think that if the orbiter flies and the rest of the elements a successful mission, you could just do it like an airplane, take down the down cargo, whatever, get it configured for the next payload that's going to go up, clean the windshield, so to speak, and the crew cabin, and go fly it again. But the rules don't allow you to do that. The rules that the other engineers that talk to you have set up are such that you have to assume that in some way, even though during the mission everything seemed to work okay, that hardware was compromised through the process of re-entering, landing, refurbishing those systems that have to be refurbished. Something may have been invalidated. So you have to test all that stuff that worked just fine in the previous mission, plus all of the systems that were not used in the previous mission, particularly the backup systems, the things that you would have to rely on in the event that the primary system doesn't cooperate during the next mission. And because of the way the orbiter was built, with its miles of wiring and thousands of components that are active components, you have to disassemble a lot of that stuff in order to meet the requirements that the program is levied on. So after the orbiter lands and you get it safed and the crew is out and you take out the payload, we spend a minimum of 2 to 3 months, roughly 250,000 labor hours of touch labor on the orbiter to do this disassembly, test, inspection, refurbishment process. Before we remove it from the hangar, take it to that vehicle assembly building, integrate it with the tank and the solid rocket boosters, and take it on out to the launch pad to go fly again. And that's where the lion's share of the work is. The work on the tank, the payloads, and the solid rocket boosters is all peripheral to the processing of the orbiter. Yes, sir.
All that extra testing you do on all the components that we're finding, do you find a lot of failures when you go through?
We find very few, very few. And you could do the trade-off of, well, is this effort worth it? But on the other hand, the few that you find, you're glad that you found them, because if not, you may not have discovered them until you got out to the launch pad and serviced your hazardous systems, or worse yet, you find out when you get in the mission. And then the impact of that could be not only a safety impact, but could be a higher consequence than spending the month to 2 months in the orbiter processing facility doing that work. Yes?
But is there a learning curve? Meaning, after each mission, do you
Yes.
learn which system you have to look at?
We look at it and say, this system is performing just fine, so we don't have to do this intense, invasive inspection and test every flight. Maybe we can just do it once a calendar year, or every 2 to 3 missions, whatever the designer thinks is the criteria for checking on the health of the system. And we've done that over the years, and after we've had a couple of years of missions where everything is working just fine, we start relaxing these requirements. And then something like Challenger happens, or something like Columbia happens, and the pendulum of conservatism swings the other direction, and we do more tests and more inspections to verify the hardware, because people want to be able to say, and we want to be able to say, well, we've done everything possible to make sure that that's 100% functional, operating, safe orbiter. And so getting this process down to where it meets the original advertising brochure, which was, we're going to fly these things every 2 to 3 weeks. You start in that direction, and then events occur either during the mission, or you have the really bad incidents like Challenger and Columbia, and the conservatism swings the other way, and you end up doing more work. And in addition to that, engineers, because we are what we are, I was one, we have all this hardware available, we like to modify it. We change it. We upgrade it because there's new technology available in computers or in composite materials. So when the orbiter gets to this processing facility, regardless of how well the mission flew, the designers, with their good intentions, say, hey, we want this orbiter to last another 5 years or 10 years, so we want you to do this upgrade to the avionics system. Or we want to change out all of the actuators that hold the payload in the payload bay, and this and that. So you modify, and that adds more time. It makes it more complexity to the process, which invites more tests and inspections. So you're constantly in a mode where, unfortunately, if the mission flies perfectly, by the time you get it and you plan your campaign through the processing facility, and I'll show the wrong way. You plan your campaign with schedules to last 2 months, maybe. Roughly a third of the work you do is work that you hadn't planned when you initially brought that orbiter into the orbiter processing facility. It's non-standard work. It's stuff that you uncover in the process of doing your test or inspection, or it's new requirements or new changes that come from the designers that have to be implemented. And from an efficiency standpoint, if you're in the manufacturing or production business, that is not efficient. If a third of your work that you laid out for the next 2 months, at the end of that 2-month period, a third of it was stuff that you had not planned on doing, which means you don't have the parts ready, you don't have the engineering, you don't have the instructions. Yes?
Do you build in time to cope with that now that you know that you need
In contingency time, yes. Yeah, we set up our operation, and let me go back to that. We set up our team and our operation to run 5 days a week, 2 shifts a day, and leaving the weekends free to catch up for this non-standard stuff. We essentially end up running a 6-day work week if we're in a standard template of flying three missions a year, which we're not now because we're still recovering from the Columbia accident. But we end up working 6 days a week, and roughly every 3 or 4 days we'll work a continuous round-the-clock 24-hour operation. So we try to maintain that original schedule, but we only make it roughly 50% of the time due to this, again, the non-standard work, the extra stuff that works its way in. And that's why, we have a big team. Our team is made up of the United Space Alliance as a contractor. They do the hands-on work. They have the technicians. They have the engineers that staff the consoles, and they're roughly 6,000 population at Kennedy Space Center. They take care of the orbiter, the tank, the boosters. They're responsible for maintaining all of our equipment that hooks into the shuttle that's required to process it and service it. And they have ties to the contractors, the original equipment manufacturers that built the hardware. So technically, they can gain access to all the original manufacturer records for the parts that are in the shuttle. The NASA responsibility, and I need to go back one more here. NASA owns the requirements for the shuttle. We've delegated all the operational work to the contractors, but it's a national resource. You know, taxpayers paid for it. Government has a responsibility. They can't divest themselves from that. So NASA owns the requirements for saying what you test, what you inspect, and what the specifications are for acceptable performance of that. That's controlled by NASA. The management of the contractor at Kennedy is done by NASA engineers in an organization. There's roughly 500 people out of the 2,000 population at Kennedy Space Center of civil service people. 500 are directly associated with the shuttle. The rest do payload work. Space station, of course, is a big work item now at Kennedy Space Center. And they're responsible for the requirements. If somebody wants to change a requirement, a NASA person has to approve that change. And we do insight into everything the contractor does. We have at each one of the, I'll get there. At each one of the milestones, when we leave the processing facility, when we leave the vehicle assembly building, and when we get ready to launch, there's a review conducted by NASA to review the work that was done by the contractor during the preceding weeks or months. And NASA approves moving the vehicle on to the next stage of its assembly prior to launch. And the launch director specifically is responsible not only for those last few days of the campaign, so to speak, leading up to launch, but also ensuring that the team, the government contractor team, has all the tools available to them to be successful. You know, is the work being scheduled in an orderly fashion? Is the budget, the ever tightening budget, constraining their ability to get their work done? Is there too much schedule pressure to meet a milestone? That's the launch director's job. So the launch director doesn't just come in the last 3 days of the campaign with the tie and the suit and orchestrate the countdown. They have a responsibility from the beginning to the end of the campaign. Engineering, I've already addressed this, but the NASA engineers manage the requirements, the changes to the requirements. They're the ones that, in addition to the contractor, this is a check and balance. They look at all of the data, the engineering results of the tests and the inspections, and they approve that they met the requirements also. They participate in critical operations. A critical operation is a test on a specific system, servicing of the vehicle for launch count, or any of the non-standard work that comes up during the process. They audit what the contractor does, and of course, because the contractor, we're the customer, they're the contractor, we have a lot of criteria to grade them on for their award fee performance. The operations people manage the scheduling. As I indicated, we like to work 5 days a week, 2 shifts a day. We really end up working 6 days a week and sometimes around the clock. So the scheduling activity is dynamic, and NASA approves all the schedule. We have to approve all the overtime. We have the authority to say stop or go, not only in launch count, but anywhere in the campaign of processing the hardware, as well as the big picture schedule. How many times a year you're going to fly and which orbiter is assigned to which payload and those missions. That's still a NASA responsibility. Orbiter processing facility, like I mentioned before, it's like a hangar for an airplane. A big part of the work effort used to be the tile. I think you already had a presentation on tile, and there's 25 to 30,000 of these little bricks glued to the vehicle. We classically damage about 100 of them on each mission due to ice and things coming off the tank that have to be replaced, but we also pull another 100 or so off just to inspect the integrity of the glue that's holding the tile to the structure of the vehicle, because a lot of those little bricks have been glued on there for 25 years, and they've flown 20 to 30 missions. So although we have offline test programs that try to duplicate the environment that the tile sees, either from a calendar standpoint or the thermal cycles of the mission. You like to go to the real hardware and see what's happening. So we do that invasive type of work of actually destroying tile, pulling it off the vehicle, just to make sure that the aging process is not causing any degradation of the system. We pull the engines out and do the maintenance on the engines offline, because the aft fuselage of the orbiter is a terrible place to work. So any of the hardware we can get out of there and do it on the bench, it's much better to do that than to try to do it in the vehicle with people crawling all over wire bundles and structure and that sort of thing. The concern about the collateral damage. To do the other work in that compartment of the vehicle where the engines are. Of course, you got to take the accommodations from the previous mission out of the payload bay and put in the new stuff for the next mission. I already mentioned modifications, and yeah, unfortunately we change more stuff than we probably should, but in order to keep up with the aging of the vehicle and the new technology, that goes with the territory of flying a system that was designed over 30 years ago. And we prepare it for the next milestone, which is the vehicle assembly building operations. This is where we put the big pieces together. The solid rocket boosters are stacked. There's 4 segments in each booster. That's a very critical process, but only takes less than a month to do that. The external tank comes in essentially ready to fly from Mississippi, except, as you know now, because of the Columbia accident, we're still looking at the ramifications of these lines and other fittings on the tank. The acreage foam on the tank, just to digress a little bit, is sprayed on, and that stuff is tough. Early in the program, we had problems with some of that coming off, but we solved that years ago. What we haven't solved is where you have to do a manual application of foam over a fitting that is there because that's where the crane's attached to it, or because there's a line there that has to be installed at Kennedy Space Center. You can't do it back at the factory. Putting that thermal protection system foam on there, it's a labor-intensive process. It's a critical technique process. And obviously there's still flaws in the process that the engineers haven't sorted out yet, and that's why that stuff keeps coming off the tank in those places. But we attach the solid rocket motors are attached to this mobile launch platform with 4 bolts, the diameter of my wrist. The structural engineers really figured this out good. So there's 4 on each one of those that are attached to the launch platform. The tank is attached to the boosters with 4 attach points, and those are bolts, again, that are diameter of my wrist. And then the orbiter is hung on the tank in 3 places with the same size bolts. So you've got 6 million pounds of weight that's attached to the mobile launch platform that's held up by these 4 bolts, well, 8 total, on the solid rocket motors, and they've worked out the dynamics of when the engines start, because the vehicle sways like this because the center of gravity is not right over where those 8 bolts are attached, and that system works fine. But it always amazed me that you could hang that much weight on those few bolts that are only the diameter of this. But it works. It works. So the orbiter is brought over after its campaign. It's hung on the tank, and we test all those connections between the solid rocket booster, the platform, the tank, and the orbiter, and that only takes about a week to do that. And if that looks good, we have a review of all of that work, and if the review says we didn't leave anything undone, that we shouldn't take out the launch pad, then we go out the launch pad.
I ask you, before you leave
Sure.
the refurbishment phase, say a little bit about how it's different from just bringing a car in to have a 50,000-mile checkup. That it's the clean room aspects, the following of procedures,
Sure.
the having a checker.
Well, a 50,000 mile checkup on a car is usually an external inspection. You know, you change the oil in the filter, and you check all the belts and the radiator hoses, and you change all the fluids. Well, you do that with the orbiter also, but in the case of the orbiter, you want to know whether you're this far away from having to do a valve job, or the rings in the engine, you know, have now got so many thousand miles on them. So we have the equivalent. You take the heads off the engine, and you give it a valve job, and you take the pistons out of the block, and you check for scoring in the block. You take the transmission out, and you pull the gears out and make sure that the synchronizers are still okay. You know, and you go through the rear end, and you take all the avionics out, or you connect the you take your carry-on test equipment in, and you hook it up to these connectors on the airflow meter and the computer in your vehicle, and you run all those diagnostics to make sure all that stuff, even though it worked fine after you turned the ignition key off the last time, that all the redundancies and all the capability is still within that hardware, and all the margins are still there. And then you button it back up, and you make sure you buttoned it back up properly.
Well, properly, all of which is pre-established, quite rigid flowcharts, checklists.
Oh yes, yeah.
A checker checking the checker.
A checker, and you have inspectors where there's critical things. If you're torquing the connecting rods onto the crankshaft, you know, it says that you got to do those bolts at 50-some foot-pounds, and the technician will do that, and there'll be an inspector there verifying that, yeah, he set the torque wrench at 50 foot-pounds, and it really clicked there, and they stamped the procedure that it was done that way.
Yeah, I want to just add to that, I mean, even more emphasis. You don't do anything to the vehicle or to the payload unless you have a written procedure. What is absolutely not allowed is, oh, there's a little problem. Something didn't work the way it was supposed to in the test. Let's just fiddle around. Let's throw a few switches and see what happens. Well, I mean, that's normally the way you work at things if you're in a laboratory or working on your car. But the thing is, you need absolute traceability, because if something later on turns up out of spec, or there's an anomaly during flight, you need to be able to recreate everything that was done to the orbiter. That's why we keep such good records on parts. I mean, if it turns out, well, you can tell that story about the tires you just mentioned. I mean, that people keep track of where all the parts in the orbiter came from, the lot numbers, and so if any problem turns up, you can actually then trace on the orbiter and see if it affects there.
It's all the procedures. All the work is done per approved work authorization documents. Every step, every touch labor item that's done on the vehicle. And if you deviate from that procedure, which is approved by engineering, you have to get engineering approval to deviate from it. The assembly process, the standard work process of putting the vehicle together after a mission, there's over 2 million verifiable work items for the standard flow, and that doesn't include modifications or the non-standard work that comes up. You know, the proverbial glitch that occurs when you're checking out your computer system, or when you pressurize this fluid system and the leak rate is higher than the specification allows. Well, that engineering comes in then and says, okay, here's the trouble procedures. Here's what you're going to pursue, but you don't do any of that until the engineers write the procedure and give it to the technicians or the console operators and say, okay, here's what you're going to do to try to find out the source of this leak. You don't just, as Jeff indicated, just start throwing switches and turning valves and say, well, let's see if we can find out what's going on here. It's all pre-approved, and the reason for that is when you have these reviews that culminate in the final review before you get ready to fly, you want to be able to say that this vehicle is assembled per print, that the designer's requirements, the people you've already heard from that certified that, you know, this system will work just fine in flight. If it looks like this when we launch it, you're trying to prove that this is what it looks like when you launch it, and it's within the certification base, and it's per the engineering drawings that we were given, and it met all these requirements. Otherwise, you're guessing that it's okay to go fly the machine, and you can't do that in this business.
Sir, so does that whole process of 2 million standard items all written down, does that
Yes.
seem to create any sort of, I don't know, tension that the engineers have, feeling like their hands are tied to go out and do stuff?
Well, no, because they're the ones that ultimately say what goes in those 2 million steps. And if they want to add more tests or checks or inspections, it's within their purview to propose that. The program, there's a group of senior engineers that are in these what we call control boards that approve the requirements that are implemented at Kennedy Space Center. And they can say, yeah, that's a good idea, or no, we don't want to change this. Go back and give us more rationale for what you think is a good idea to do to this system. So in that respect, it's probably somewhat frustrating for the engineers because they can't do anything different than last time unless they can justify the rationale for it. But that's the way it ought to be. That's okay. The launch pad. It's the facilities at the launch pad are pretty simple. These are the same launch pads we flew from in Apollo. We've got storage facilities for the liquid hydrogen, liquid oxygen. We try to spend a minimum amount of time at the launch pad because Florida's a nice place to be on spring break, but it's a bad place to have exotic hardware sitting outdoors with all that salt and humidity and the other elements that Mother Nature throws at you like lightning. And you can see on the, well, I think you can see down here, we have a good lightning protection system. There's a single mast with 2 wires that go out about a half a mile from the launch pad. It makes a good Faraday shield. And over the years, we've been whacked a lot of times with lightning. In fact, it's a good attraction for lightning, and we've never gotten enough energy inside of that Faraday shield to damage any hardware. However, when we get lightning down there, we tell the workers to stand down and, of course, seek safe haven. But we've instrumented it, and it's taken some big hits, but we haven't gotten anything major inside that would cause us a problem from electric. Yes.
After you take the shuttle out to the launch pad, is it very expensive to roll it back when you find a problem and then bring it back up?
Yes, it is, and that's why we have these reviews before we commit it to go to the launch pad to make sure that we're not taking any unknowns or any work out to the launch pad that should rightfully be done either in the vehicle assembly building or further back in the orbiter processing facility. So yeah, it's a lengthy process because it takes about a week to hook everything up at the pad and check it before you go into the process of servicing the propellants and doing the hazardous work, which has to all be undone if you roll back to the vehicle assembly building. So you got to make sure you're really ready to go before you head on out there. Yes.
Approximately how many times does that happen?
The going back to well, we probably have done it for technical reasons, maybe 20% of the time. For weather reasons, like we're worried about, a hurricane or something like that, the same, about 20% of the time. 1 out of every 5 times we've gone to the launch pad, we've had to come back for either a weather problem or a technical problem that either occurred at the launch pad or it's something that happened with a different vehicle in the fleet that may still be in the orbiter processing facility, or a component that's similar to one that's on the shuttle that's at the pad that they were doing testing in a laboratory or doing what we call fleet leader testing at one of the NASA facilities. And they said, there's an inherent flaw in this auxiliary power unit. And we have to change the ones that are in the orbiter because they were manufactured at the same time or they have the same component on it, and you can't do that work out at the launch pad, so you got to roll it back. So the hardware at the pad may be just fine, from the standpoint of that you followed your processes and it checked out. great in the previous part of the campaign, but an offline issue can cause you to say, nah, we got to roll back and go change out this hardware or fix it or further test it before we can commit it to go fly. We have a big water tower out there also, which I'll talk about later. That's our sound suppression system. But basically, at the pad, a month is the maximum time you like to spend out there. Usually now, we used to put a lot of payloads in the orbiter processing facility when we were flying laboratories and that sort of thing, space station hardware. We install all that out at the launch pad now. And we have, we test all the connections. We're, a new facility. And we have a simulated launch count with the astronauts, and this is a tradition that goes back to the Mercury program. You bring the astronauts down to the Cape. They go through a day, 2 days of training, emergency egress, familiarization with the hardware, and then we have a simulated launch count without the propellants and all the hazardous stuff. Just to remind, if nothing else, to remind the launch team that this is more than just a machine. We're going to fly people in this thing, and this occurs roughly 2 weeks before launch, and it's a good readiness test for the whole team. It's serious. We're a couple weeks before flight. The crew's in town. This vehicle's going to look the best it ever has, and we do a simulated launch count down to within a couple seconds of liftoff, and then we do a simulated abort with the safing of the vehicle, and the crew gets out.
Yeah, I'll just add something, because that's always something the crew looks forward to. First of all, because you actually get in the vehicle, which, despite the fact that we have pretty good simulators in Houston, there's nothing like actually crawling inside the shuttle that you're going to fly in. And there's a lot of safety training that you do down at the Cape, which is really kind of fun. I don't think you don't have any pictures of the launch escape.
Oh, the slide wire
the pad
baskets?
slide wire.
No, I don't.
There's a requirement that you need to be able to get off the pad quickly if there's a launch emergency. And of course, on the real launch day, unlike the simulated countdown where the pad is crawling with people, on launch day, there's very few people, even when you're getting into the vehicle, because it's fueled, and then everybody else leaves. And so they have this big slide wire where if you have to get out of the orbiter in a hurry, you go out and you jump in the bag and you hit a little guillotine and it cuts you loose and you slide all the way down. Actually, in the early days, the astronauts kept saying, well, we need to try this out. And they said, no, you can't do it because it hasn't been man-rated. We said, well, wait a minute. They said, well, it's rated for emergency use only, so you can't try it out. But the other thing, and then after Challenger, they insisted that somebody actually ride down in it. And normally we don't. But the other things that you do, no, just one person tried it out. But the other things that you do, once you get down to the bottom, there's an underground bunker that you run into, and either you stay there and wait for help, or they have these armored personnel carriers sitting around there with a tank, little tanks, which you get in, and you've got to be able to drive your tank. They have a breakout section of the fence, so you drive the tank through the fence out to a helicopter pickup point. So we all have to go out and learn how to drive the tank, and we drive over the sand dunes and everything. And then they also they have a big pool which they light on fire, and they give you a big fireman's hose, and they show you how to make your way through a fire by squirting a water path in front of you. And it's all the little things you dream of as a kid. It'd be a fireman, drive a tank. So it's good fun, but it is part of the the extensive safety procedures that they have, and all these things. Periodically, they have to exercise, so they do go through every once in a while a disaster drill down at the Cape where they simulate an emergency where they have to pick up the crew either outside the launch pad or even out in the ocean, and you got to keep people at full operational readiness. So anyway,
that's one of the aspects of training is we train for the anomalies, the non-standard things. The standard work, they do so much of that anyway. You don't have to train for that. You don't have to train to put a payload in a payload bay. You don't have to train to power up your system and run your systems checkout, because that's a repetitive thing. But the non-standard stuff, when things go wrong, that's where the emphasis of the training is. And it's, like Jeff said, it's a lot of fun. It's fun for the launch team too. We have a control center at the Cape, and it's called the Launch Control Centers, which, so you would think, well, this is where you launch it from. Well, you do that, but all of the other work that's done in the preceding 3 months is controlled from the Launch Control Center by test conductors and engineers who wrote the procedures and the software that implement all the requirements. And they control the activity on the orbiter or the tank or the boosters when it's still back in the offline facilities of the vehicle assembly building and out the launch pad. They do it from the Launch Control Center. We automate what we can from there, but for the manual activity, and a lot of it is manual because regrettably you can't do all this refurbishment on the shuttle with automated systems. It wasn't built that way. It is all managed from our Launch Control Center with old computers, but with a great team of people. I'm going backwards here. Yeah. The software we use and the computers, I'm not going to go into a lot of detail, because it's really, I mean, it is old stuff, but it works, and it's like the software programs that the FAA uses to track airplanes. You know, it's hacker-proof. There's no external interfaces outside of the Launch Control Center firewall. It works just fine, and that's where we do the management of our day-to-day operations from our launch control room, and we call it the LPS, Launch Processing System software. We've tried to change it a couple of times over the years, buy new hardware. We have supplemented it with laptops so that we can do more human engineering displays, but the computers are the same ones that we bought back in the late 70s. But then so are the computers that are on the orbiter that fly the machine, and it works. This is a bit repetitive, but I want to go through it again to make sure to emphasize what the role of the engineering is. The designers that you've heard from, they certified their design, and they did extensive testing. They just like Detroit does on a car, on the door latch, and they have tested that door latch and said, well, this thing ought to be good for 250,000 miles or 20 years or so many gazillion, opening and closings of the door before it wears out and you got to replace it. Well, they did all that. And to make sure that that hardware is still within the certification base, they develop requirements, send them down to the Cape. We put them in procedures, either manual procedures or software, to implement those requirements. And the team, United Space Alliance, the contractor, and the NASA engineers will certify at each of the milestone reviews in the process of moving the hardware out to the pad. They've met those requirements. And they did that either by participating in the activity or by reviewing the test data. And that allows us to sign a certificate of flight readiness a few days before launch that all the requirements have been met. When we get into launch count, we've taken a subset of those requirements that, when everything is powered up and ready to go fly, all of these systems that are active ought to look like this. The voltages should be between, this upper limit and this lower limit. The pressure should be between here and here. These indicators should show that they're open, and these indicators should say that this latch is closed or the valve is closed or whatever. And we put that in what's called launch commit criteria. And that's the acceptable limits for the performance of that hardware when you're at that point, which is 9 minutes before launch, when everybody commits that they're ready to go fly. And all those requirements, again, are implemented by procedures and software, and the 3 days of launch count have roughly, these are numbers, but about 500 requirements. There's thousands of measurements associated with those requirements, and most of the looking at those measurements is done by computers, obviously. But you have the engineer involved, because if it's not within limits, you turn to the engineer for, what's wrong, and is there any chance to go fix this, or do we have to change hardware, we have to do troubleshooting. So it's not a hands-off operation, obviously. Going backwards. The structure of the launch team, the launch director shows in the middle, but that doesn't mean that he or she is, the only one with a go or a no-go button. The engineers, the people that implement the requirements, there's roughly 150 of them in our control center, and they're the ones that provide the go, no-go for all the subsystems, both flight and ground, that everything's operating within the limits. They report that to a team of test conductors, NASA and contractor, and that's reported to the launch director. You also have, we're not alone, obviously. We have an engineering support area, which are all the hidden senior engineers that you don't see on television, and there's a room full of about 150 to 200 of those, and they're looking at the performance of these systems as they're activated in launch count. And they've got all the trend data, the previous history of it, and they're looking at things like, well, all right, everything's in limits, but is it within family? The last time this system performed, the voltage was this or the pressure was this. Well, it's still in limits, but it's not the same as it was before. So we go look at it. Go look at more of that. Well, that's for this group of engineers over here. These guys and gals are running through their procedures, and if everything was within limits, we just turn the next page and go on to the next one. And they also have the emergency procedures. If something bad happens, these are the people that will implement the emergency procedures. But this offline support, they're out there, they're the senior people, they've been there before, they've been out there who knows how many years, and they're asking questions like, well, that didn't look right, or, we missed that step. Go back and check it again. That's what they're for. The mission management team over here, these are the people that do the certificate of flight readiness. These are the folks that stand up in the readiness reviews and say, I gave the Cape folks a good set of requirements. There's nothing that happened with the hardware that they're responsible for in all those offline facilities or on previous missions that should have any cloud over this mission. They're responsible for certifying that, and they do that through a structure of the mission management team. You've got, of course, the flight director has flight rules, and the flight team that they look at during the launch count process, and you're going to hear more about that from Wayne Hale. Good. And they obviously have a go, no-go input to the launch director in the decision process also. We have an integration activity that looks, the system engineers are each responsible for, they have boundary conditions on what they're responsible for. It's these pieces of hardware, it's this wiring, it's these actuators or latches or whatever. But a lot of that stuff fits together. Integration, technical term for making sure that this person talks to this person and they're hooked in with this one. That activity is done by a console in the control room, again with senior engineers who actually manage all the automated software that runs the last couple hours of launch count, that really launches the vehicle. And they're tied in with that. You also have the more subjective stuff. We launch on a public range. Public safety is obviously an issue, so the range has to make sure that it's safe to fly from a public standpoint. There's no boats in the launch danger area, no airplanes, and that the weather meets the criteria of being able to track the vehicle should it go off course. And of course the payload has to certify that particularly if there's an active payload, that all of their launch commit criteria is met. And last but certainly not least, you have safety oversight of all of that activity. And what I don't show on there, of course, is the flight crew, but they're obviously in communication with all of these people. So that's the network. But everybody out here has no-go authority. Anybody can come on the net or press their switch and say, hey, I got a problem, we're not going anywhere. And it's the launch director and the launch team's responsibilities to make sure that problem is addressed, hold at the convenient, graceful to stop all the activity hold point until the issue is resolved. The real job, and I'll get into this later, of the launch director is to say no when everybody else wants to go, because as you get further in the launch count, the launch fever process sets in. It's a natural. Got it. It's a natural thing, it seems to be. People want to go.
I want to ask you about that a little bit. I know we'll get into it later on. Flight rules and the launch decision. There are flight rules that say you must scrub if these conditions are not met.
Right.
And yet there is a tendency to allow judgment to come in. Let's take an example of a limit on crosswind at the landing for the return to launch site. You see it go above limits. If you look at the rules strictly, it says no, you can't go. Talk about that a little bit.
That's what we use the mission management team for. If there's, and you bring up the weather example, most of the stuff is pretty straightforward. It's either the voltage, pressure, temperature is in limits or out of limits. Person can question that, say, I don't like the trend, and you've got to stop and clear the air if they say, I want more discussion on this, I want more data review, and that sort of thing. That's when we revert to if it's a discussion like that that involves activity outside of the control room, beyond the purview of the console operators that are running through the procedure. We rely on the mission management team to manage that activity. So the console operators can concentrate on their launch commit criteria and their procedures and their software. So something like crosswind limits, if there's a debate with the flight director and the weather people, we hold the clock and say, mission management team, that's yours. You manage it, and whatever you have to do to resolve the decision, we'll scrub if need be, we'll hold if need be, or if the community can get comfortable that these crosswinds that are peaking occasionally out of spec, that's okay to go fly anyway, then we'll wait to hear from the flight director that that's okay. But we don't insulate the control room from that, but we don't want to burden the control center with working what is an offline issue. And it's up to the mission management team to disposition that. And you bring up weather because weather is one of the few things that there's really a lot of judgment still involved in. Is the weather good enough to go fly? And it's probably the only thing that's in that category, because everybody has an opinion on the weather. And Florida weather's dynamic, and there's usually, unless it's wintertime, there's clouds, and there's always a tendency, if you've held for weather or the weather's marginal, to hold longer to see if the weather gets better. And the real issue for the launch director is to try to convince people, if the weather's good enough, then this is good enough. And yeah, you could wait longer for it to get better, but it's good enough. We're running out of window time. All the time we sit here on the ground with all these systems, humming along, the probability of some glitch or something coming up to scrub you is increased. So, and just, as a personal note, when I was in the Air Force, I was a weather forecaster for missile operations. And I felt that was a waste of an engineer's time because, I was a graduate engineer with my diploma sticking out of my pocket. I wanted to go launch missiles and rockets, and the Air Force said, no, Lieutenant Sieck is going to be a weather forecaster supporting missile and operations. So I endured that for a couple of years and put all of that experience in my hip pocket, and I didn't need it until I got in this launch director job. And I spent many hours talking to the weather people who provide the forecast for the launch, going over all of the data, and the technical aspects of the weather situation to see if if it was prudent to sit here any longer and wait for the weather to improve, or whether it's better to scrub, get these guys out of their uncomfortable suits and send them back to crew quarters and recycle for the next day. And I didn't
So flight rules don't necessarily...
They won't necessarily scrub, but you have to disposition their concern, and you will hold until their concern is taken care of. Yes. Yes.
This is unrelated to what we've been talking about, but you know how the Russians have, in going out to the launch pad, they use a rail track, and they have the rocket flat. Can you do that with the shuttle instead of stacking it like this and then rolling it out? Would it be better, easier? Was that ever considered?
Well, the problem with that is the solid rocket boosters. You know, they weigh approximately, when they're assembled, a little less than 3 million pounds apiece, and the joints that caused the Challenger accident are, you know, they're critical. And I don't know if they went through the technical aspects of the design, but these things are 14 feet in diameter. You know, each segment weighs 300,000 pounds, and they have these two clevises that come together with O-rings in there. And what caused the Challenger accident was there was rotation in these joints to the point where the O-rings, because of cold weather, weren't making a good seal, and it caused a gas path, and it you know, 1,200 degree temperature exhaust plume just cut through the metal once it found the path. So you want to maintain the integrity of these joints. So if you stack them horizontally, and that could be done, and then you lift this thing vertically, the joints aren't certified to maintain their integrity doing that. Plus you'd need some kind of huge crane to, you know, pull this, you know, 3 million pounds from horizontal to vertical. So it's
something that could have been done had it been built into the design at the beginning. And the Russians have a tradition of doing this,
yeah.
And so that's the way they design their rockets. You know, for whatever reason, we never started that way.
No.
From the very beginning, our rockets got stacked vertically, and that's the way all of the American rockets have been designed.
Yes.
For the launch director, I mean, is the launch director ultimately accountable for saying flight-worthy shuttle or no?
The launch director is, whether it's flight worthy, actually that mission management team is responsible for the flight worthiness, because they encompass not only the, you know, watching what you did in launch count, but the certification of all this hardware before it even got to the launch pad. And ultimately, the launch director is responsible for conducting an orderly launch and making sure that this mission management team doesn't have any issues, that engineering team doesn't have, that the console operators have really completed their procedures. That's their responsibility. And if there's any fuzz on that, so to speak, even though console operators say they're go and mission management team says they're go and flight says they're go, if there's any concern about that, it's the launch director's job to say, no, we're not going to go fly today. You know, I'm going to give you another day or 2 days to do more homework, look at more data, have more discussions. We're going to scrub today, even though everybody may say we're go. And that's happened before, you know, and I always wondered after, and not too many times, when I've said no and everybody wants to go, whether I get the phone call and saying, well, I'm glad you made us safe today, Sieck, but you don't have this job tomorrow. You know, well, I never got that call. Never did. The process, not to bore you with, but since it's an operation, normally we try to launch in the middle of a week, Wednesday or Thursday, so we usually take the weekend off before that to clean up everything, give the launch team a rest. So we power up everything, and that's the way we start the process, and that's a couple of shifts worth of work to bring up the ground systems, the flight systems, make sure that all the avionics hardware really comes to life, and we put in a no-work hold at the end of that to take care of any problems. If that all goes well, then we get into the more critical activity that has time constraints associated with it. We load the fuel cell, that's the power plants and the orbiter, reactants, liquid hydrogen, liquid oxygen, because they have limited life. Even if you don't have the fuel cells activated, that stuff boils off and you lose it, and that could count against your mission capability. And that's a hazardous operation also. And then we put in another no work hold at the end of that. And then we have a period of time where we do the final, bring up the final systems, put in the time critical stowage, particularly when we're flying laboratories and you put in, plants or critters or whatever it may be in the either in the crew module or the payload bay. And the last 12 hours down here is when you really got to make sure this is a real decision point right here. Are we going to load the external tank, put a cycle on the tank, which and we know that putting liquid hydrogen and liquid oxygen, there's roughly 500,000 gallons in the tank, has its puts stresses into the hardware. You really don't want to do that unless you're pretty sure you're going to launch that day or that night. So we have a meeting before that to make sure the weather looks pretty good, that the mission management team is not working any offline issues. And that's happened before. A war story for you. In the early 80s in one of our missions, we assembled the mission management team to decide whether or not we ought to go load the external tank and go fly. Everything looked pretty good. And the orbiter project manager said, well, I need to make you aware of this. I just got a fax, a telegram from the manufacturers of the tires. And the manufacturer said they were inspecting a lot of the tires, of which we have 2 of them from the same lot on the orbiter, and they found some blems on these tires. And they don't know whether it's a manufacturing flaw or an aging defect, and we don't know whether it affects the integrity of the tires. But since we knew you were launching tomorrow, we thought we would share this with you. Warm regards, B.F. Goodrich, or I think who it was at the time. Well, and so, the mission management team threw that on the table and said, hey, we got to go work this. These people, we don't know. They haven't said they're not certifying the tires. They just said they got a problem. So we say, well, that's fine. Mission management team, you go work that, and let's talk about whether or not it's prudent under these circumstances to go load the tank with some probability that we get all the way down to T-minus 9 minutes, and you folks are going to say, hey, we need to look at more test data on these tires or have more discussions with B.F. Goodrich or whether let's not go fly today. Well, you don't want to load the tank and go through all that if that's what you think the situation is going to be, 8 hours away from that, and you've put a cycle on the tank, you've used up a lot of cryos that you can't save because of the heat leak, plus your launch team has put a cycle on, depending on the time of day, they've been up all day, all night, or whatever. So that's the kind of issues that you need to make sure get worked. And the mission management team has to handle that, but the launch director has to decide, nah, you just go work that for another day or two. We're not going to load the tank. Or what's the promise of this coming to fruition, the possibility so that it makes sense to go try to fly.
So what did you do with the tires?
They had, in that case, we went ahead and we tanked. The subsystem manager for that, which you may have already heard from, went back to a lot of the test data that they had run on the tires that had been fairly recent. Langley, I think, was involved in it, and they said, we don't have to worry about those blems being a problem for the tires that are in the orbiter, which, by the way, you don't have any access to at the launch pad. If we were going to change the tires, you'd have to roll back to the orbiter processing facility, and that would be a couple of months worth of impact to that flight. So we ended up not doing anything with the tires, but it had the mission management team really busy for about 8 hours. So, and this process takes about 3 days, and we have refined those procedures, as you might expect, over the years to make this as an efficient and a repetitive a process as we can. In addition to minimizing the hazards to the people and the equipment. At the end of the tanking, I'm sorry.
Before we go to terminal count, usually
Yeah.
we take like a 2-minute break halfway through.
Yeah, this is a good time to do that. Oh, yeah. No, that's same, yeah. Okay. Terminal count phase. Well, we call it terminal count. After the tank is loaded, 500,000 gallons of liquid hydrogen, liquid oxygen, and there's no leaks, and we have leak detectors all over the vehicle, and we've scrubbed a lot of launches because of leaks. We give the crew a go to come on out, and if a crew of 7 or 8 people, it takes an hour and a half. Get them all in, get them connected, check their communications and that sort of thing. So roughly 3 hours before launch, we bring them out, we get them all connected, we close the hatch, and we verify the integrity of the crew module. And we're at clockwise, we're down to T-minus 20 minutes. But if it's a rendezvous window, and most of them are now, the launch window is only 5 to 10 minutes long. So we have to be in phase with the same plane that the space station is in, and we've got to get in phase with being able to catch the space station or have it catch us. So, the launch window is, we don't have enough energy in the shuttle to steer to any orbit we'd like to. So the launch window is only about 10 minutes long. So we put in a long hold at T-minus 9 minutes for those kind of missions. It's the equivalent of the 2-minute timeout in a professional football game. Everybody has a chance to review their information, discuss their strategies. If it's a long launch window, if it was just a lab mission, then we only wait for 10 minutes at this T-minus 9 mark. But if it's a short window, we set up the clock such that we hold there for almost an hour. And then we do, as you saw on that previous chart, we do a poll of all those people, make sure that they're still go and they're not working any problems or issues. And then we start this automated software program that looks at, in addition to the systems engineers and their consoles looking at all their information, we have an automated program called the ground launch sequencer that looks at all the measurements, all the parameters to make sure that they're within limits. And it issues all the commands to the vehicle and the ground support equipment. And we did that so we could manage the repeatability of that process. And to take the human factor, button pressing out of the process as much as possible. And there's not a lot of work that goes on in there, and there's very little manual work. At 5 minutes, the orbiter access arm, their ability to get out of the vehicle in a big hurry is retracted. It takes 2 to 3 minutes to pull that back, but we can get it back up to the vehicle in less than 30 seconds, which is, it's about the amount of time it takes them to unstrap and get out of there anyway if there's a fire or something bad like that they have to do an emergency egress. They start the propulsion units on the orbiter that pressurize the hydraulic system. Just like in an airplane, there's an automated test of all the aero surfaces, like they do on the end of a runway, but this is done by the computer, and it wiggles the elevons and the rudder and the main engines to make sure all of that works. And we also start the conditioning of the propellant at the engine interface. And if they already had the discussion about the main engines, you have to make sure that the quality of the fluid in the external tank and the quality of it that's right there at the injector of the engine is within the temperature and density parameters that the engine was certified at, because we have to drain the propellant out of the fill lines. And once we've started doing that, that propellant starts heating up right there on those valves that are going to go into the injector and start the main engines on the orbiter. So that limits our ability to stop and hold after that. We're good for 4 to 5 minutes after that starts, and that process starts at T-minus 5 minutes. After that point in time, we're either going to launch or scrub in the next 10 minutes. And then we pressurize the oxygen tank and we pressurize the hydrogen tank. But anywhere in this period of time, we can stop if an engineer or the automated sequencer says, something's out of limits. We'll stop at those milestones and disposition that problem if we can. But per our rules, we won't waive any requirements at that point, even though an engineer may have a perfectly good explanation as to why this temperature, pressure, or whatever, or limit is not being met. If the launch commit criteria, the launch rules say no, it has to be like this, then we're not going to go launch that day. We won't. After 31 seconds, the solid rocket boosters come to life. The propellant doesn't ignite, but their hydraulic system is powered up. Their avionics systems are powered up. Their engine nozzles are checked again in an automatic sequence. And at 10 seconds, if everything looks good and all these measurements that our ground launch sequencer has been looking at, we send up the computer data bus a go to the onboard computers that said all of our stuff has been satisfied. Now we're still looking at a few things. We're looking at those bolts that are holding the solid rocket motors to the launch pad and the ability to blow the nuts that are holding them. Should that system fail, we would send a cutoff to the onboard computers, regardless of where the engines were in their startup system sequence, the three main engines, everything will stop. And hopefully it'll gracefully come to a stop, and we'll safe all the systems and go from there. But that's the final handshake, but that's pre-planned between flight and ground, is at 10 seconds when we send a command up to the computer, say, we're all go. We can still shut you off, and we can shut you off manually too. If a console operator sees something happening that they think could be, compromise the safety of the launch, they can call for a cutoff, and we have a switch that says cutoff. It sends a command to the onboard computers, and it'll stop everything within 10 to 20 milliseconds. But you don't like to put humans in a position to have to make that call, and that's why all of the critical stuff is done by the computers. And I mentioned the ground launch sequencer. That's the console and operators in the back of the control room. And they're the ones, by the way, to determine nobody presses a button for launch. A woman in the back of the control room types the liftoff time into the computer when the launch director tells her, hey, looks like we're going to come out of our T-minus 9-minute hold at this point in time. So here's the liftoff time. Put that in the computer. And after that, it's a hands-off operation.
Can I ask how are these commands being physically sent? I mean, they're hardline cables.
It's a hardline. It's what we call a launch database. It's a cable that's connected from the computers in the control room through the liftoff umbilical into the orbiter computers. It's a data train, and it's a.
And when is that connection broken?
At liftoff. At liftoff. The onboard computers, we'll check the health of the main engines, and if the three main engines are within all of their operating parameters, the turbines and the pumps and the temperatures, then it sends a command to those 8 bolts that hold the solid rocket boosters to the mobile launch platform, and the bolts that hold the external tank vent arm to the tank, and the 2 orbiter umbilicals that says fire the nuts, we're going to go, and that's orchestrated by the onboard computers. And when that happens, you're flying, you're going. The command to ignite the igniters on the solid rocket motors is sent at that time also by the onboard computers within a couple of milliseconds. So all that happens at once. And it's an onboard automated thing. I talked about the human factor. The repeatability is important, and we, I mentioned, I gave the engineers I always threw rocks at them because they always want to change things. It's the launch director's responsibility to manage. They're the owner, so to speak, of the launch count procedures, the 5,000 pages of documentation and the 500 or so software programs that are executed in the launch count process. And we discourage changes to that for obvious reasons. Unless there's a modification to the flight hardware or the ground hardware, or we found something in our previous launch attempts that said, that we need to fix this, or there's an opportunity to increase the margins, we don't change it. we try to maintain that the procedure and the hardware the way it's always been, and it essentially is. We do training, obviously, but we train for the non-standard work. You know, it's just like in the flight team. You know, we have a simulation supervisor that throws diabolical failures out there, and we have a computer programs, and we bring the control into the control center. We bring the launch team, power up the consoles, and their displays look like, you know, the shuttle's at the pad and it's getting ready to launch, and we throw failures at them to test their reaction and to find bugs in our safing procedures, and we've done that over the years. I think in the next generation of vehicles, we'll probably have more automation, and that'll probably be a better thing. But you'll never take the console operator out of the control center, either the launch control center or the flight control center. You need the person there to disposition the problems. But predictability is what we're always after. You know, and stable procedures, be they flight or ground, give predictable results, and that's why we automate, and we control change too. Responsibility. Excuse me, losing it. I talked about the engineers. Didn't mention, I don't think, technicians and inspectors, but when a technician stamps a procedure that I torqued that bolt, and the inspector stamps that same procedure and says, I saw him torque that bolt, that's their warranty that event really happened. And that paper trail and that warranty is very important. When an engineer signs a procedure that tested the flight control system, it said, I reviewed all the data, didn't see any glitches, everything met specifications. That signature is his or her warranty that the procedure ran correctly and that they understood the requirements that were implemented by that procedure and the requirements were met. And that's important. You know, our whole concept of launch readiness is based on people being responsible for their system. Be it the designer that signs it that says there's nothing going on offline, there's no faxes out there that says there's a cloud over the tires, you know, or my last test of the main engines at Stennis, there was nothing there that says these 3 engines that are on this orbiter shouldn't work just fine, and they do that in the flight readiness process. That's their warranty and responsibility, and we hammer this home. And it probably comes from, I had this quote in my office for years, and I'm gonna bore you with it, and maybe some of you can guess where this came from. Responsibility is a unique concept. It can only reside in a single individual. You may share it with others, but your portion is not diminished. You may delegate it, but it is still with you. You may disclaim it, but you cannot divest yourself of it. Even if you do not recognize it or admit its presence, you cannot escape it. If responsibility is rightfully yours, no evasion or ignorance or passing the blame can shift the burden to someone else. And this is what we push home. And by the way, this quote, anybody? It was Admiral Rickover who was testifying before Congress after the first nuclear submarine accident. And he was saying, I'm responsible. It's my program, it's my submarine, I'm responsible. Even though somebody else was commanding it, it doesn't matter. I'm responsible. And we impress that on the managers, the engineers, the technicians, the inspectors. You know, you're important, and the work you do is important, and when you sign or stamp that procedure or give a go on the net, that's your warranty that everything is working and you understand the requirements. Very important in the business that we're in. decision making. And on the chart that this structure has been in place since the Mercury program. You know, there's nothing new here. And the only issue comes in when there's a gray area. Who makes the call, and how much judgment is involved in the call? And I mean, I gave you the example of weather. You know, weather can be, everybody has an opinion on it. It can be judgmental. Well, the weather decision is, if it's launch weather related, it's the launch director's responsibility to determine if it's good enough. If the flight director has an issue with the return to launch site winds, and that ultimately is his or her decision. These people may get involved in it, and they may have offline discussions with the flight director, but it's still ultimately his decision. And that's the way it has to be, because they're responsible. This mission management team is not responsible for the go no-go decision on weather on launch day. It's the flight director for the flight stuff. It's the launch director for the launch-related stuff, and it's set up that way. So there's no fuzz on it. Other people can have an opinion. Other people can have input. But unless this person up here says, launch director, we're no-go, it's the launch director's decision in that case. Communication. The real important. And I'll give you an example of that. The Apollo 13. Most of you probably don't remember Apollo 13, but Apollo 13 was like Challenger and the Columbia, except we didn't lose the flight crew. But it was just as disastrous an event, and by all rights, that the crew shouldn't have made it safely back to Earth, but thanks to the heroics of the flight crew and the flight team and the timing of when that event occurred, they were able to get back home. But that was all caused by activity that was done on the ground well before the launch. And specifically, since I was involved in that, I remember this like it was yesterday. Of course, part of that is an old age thing. Stuff that happened 40 years ago comes in loud and clear. Stuff that happened 4 days ago, I have a hard time remembering. But this is. But we had a tank in the spacecraft that we ran our simulated launch count, and back then we put propellants in the vehicle, all the hazardous stuff, and detanked. And we couldn't detank the liquid oxygen out of this tank that fed the fuel cells on the spacecraft. And just a little more history, the tank had been dropped when it was installed back in California, but engineers and managers did some tests and some rationale on saying, well, it's still okay to install it. So we got it down the Cape, we put the liquid oxygen in it, and all the rest of the system. We couldn't get it out of this tank. And after reviewing it, they found, well, there's the standpipe in there that you use to drain it on the ground is probably bent or damaged, and that's why we can't get it out. So the managers and engineers got together for a few days and said, well, turn the heaters on in the tank and vent the liquid oxygen off, heat it up, and it'll boil off as oxygen gas through another loop that takes it through the fuel cells and out a vent on the vehicle, and use the heaters to go do that. So they developed a procedure, and we went on station a night, a week after we had the anomaly, and turned everything on and turned on the heaters, and it's fine. You know, you can see it's turning, the liquid's turning to gas, and it's coming out. And the console operator in our control room says, hey, Sieck, I can't monitor the temperature in this tank anymore. Well, why is that? Well, the range on the temperature is from ambient down to minus 300 degrees because it's measuring liquid oxygen. And it's upper limits. You know, it started heating up, and now I can't tell you whether it's, 50 degrees or 350 degrees. Yeah. I said, okay, stop. So we stopped the test. got all these managers involved, including the people that built the tank, and said, hey, you know, we've lost visibility. We're putting energy into this tank that has liquid oxygen in it. We can't monitor the temperature anymore. Pressure seems to be fine. They said, don't worry about it. There's a thermostat in there. It's heat sensitive. And it'll open up the power to the heaters if it gets to some limit in there. Just keep your eye on the pressure. Make sure the pressure doesn't get too high. Well, of course, the pressure isn't going to get too high because the vent is open. So we said, fine. So we turned the ground power supplies on and let the thing cook for 10 to 12 hours. And what we didn't know was that that thermostat wasn't certified to the voltage we were using from our ground power supplies, because we didn't tell them, although our requirements allowed it, that we'd crank the power supplies up to 50 volts. And why did we do that? Well, the more energy you put into the tank, the hotter the heaters get, and the quicker the liquid oxygen boils off. You know, high school physics. So, but we didn't tell them that. And the people that built the tank and built that thermostat had only certified it to the voltage the fuel cells supply, which is half that value. So the thermostat welded together, the points did, and we had continuous power going on in there for 8 to 10 hours. It got to 800-900 degrees in the tank. We burned all the insulation off the wires to the fans and the heaters. And from that point on, we're just waiting for something to happen to make those wires come together, and if you then turn power on, you're going to get a spark in an oxygen tank. Not a good thing. Well, that's what happened a day into the mission when they were heading to the moon. And they turned the heaters and the fans on to stir the cryogenics because they were worried about stratification and zero gravity. And they got the spark, and it blew up the service module. Point is, the communication, we wrote down in our procedures what we did, but we didn't communicate that on a real-time basis. And although we reviewed the procedures afterward, as the rest of the team did, the designer, who was 1,500 miles away, who had approved what we did over an intercom system, didn't review our paperwork, said, "How you hit that thing with 50 volts. It's only certified for 25 volts, even though our requirements allowed us to use 50 volts." So it's a case where requirements didn't, preclude us from launching hardware that in hindsight was flawed. But on the other hand, communication, we didn't tell them in real time. And as a result, Apollo 13 happened. So I learned that lesson early on. Even if you're boring them with what appears to be minutia, you're going to tell them everything and document everything. And thankfully, they went through our procedures and they said, well, there it is, And I thought we'd get fired, and actually we got patted on the back for documenting what we had done. So it made it easier to zero in on the root cause of the problem. And as a result, we fixed that, and we were able to fly again in a few months, as opposed to having to go through a Challenger or Columbia type of activity. Very important. Launch fever. The human factor, and it's hard to describe what the environment is in the spacecraft, a few minutes before launch, or in the control room, but there's a lot of tension and there's a lot of energy, and everybody in there for the most part has been awake for the last 10 to 12 hours, and they came to work that day or that night with all hopes of safely launching the space shuttle, and they really don't want anything to go wrong, with their system or somebody else's system. That's the mood, because if something goes wrong, you're going to come back tomorrow or next day or next week. So they really want to hear this. Everybody, when they do the polls, say go, 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 go. And the hardest thing is saying no when everything sounds like it's go. And there's a lot of times when the launch, we've had problems with ground support equipment. It's old. I wish we had all new stuff for Shuttle. A lot of this stuff is the same we used on Apollo. And in spite of our efforts to maintain it, it's all out in the corrosive, atmosphere at the launch pad. And that stuff constantly gave us problems. And we would lose some of our redundant systems and some of our primary systems. And more than once in launch count, when we'd have a problem out there, the team would come to the launch director through that, organization chart you saw and say, hey, we got an idea. We think if we patch around this and then hook this up to this and we throw these switches and we get this result, it'll be okay. And we can go fly without this power supply being active or this purge system operating normally and all these other things that we've got out there. And what you have to do as launch director is say, well, is sit back and analyze whether or not, you rely on your engineers to use their Yankee ingenuity to fix a problem, but you have to assess whether or not they're literally, shotgunning it and coming up with a proverbial quick fix because they want to go home in an hour or so and celebrate a good launch. It's just like these guys want to get out of those uncomfortable suits they've been sitting in for the last couple hours and either get out of the spacecraft or get up there in zero G. So as a launch director, you have to assess, well, okay, but is this really the right thing to do? Are they working this too hard? If you gave them another 24 hours to look at the data and think about their approach to a fix, would the answer be any different? And there's been a few times when they said, well, yeah, that sounds pretty good right now, but I'm going to give you another 24 hours to think about it. So we're going to scrub for the day, and you can hear the big groan in the control room, and you can just see it going through their heads, this guy's lost confidence in us. We all came to work, we get paid to solve problems and get things done, and he's telling us that ain't a good answer, ain't a good fix. So you have to balance that when you're in charge. But the real job of the launch director is to say no when everybody else wants to go. That's really what you're there for, because everybody else, these guys, Jeff, they get tunnel vision, they want to go fly. The console operators, things are on automatic, in that last 9 minutes, and they just hope they don't get that little red or yellow light on their screen that says, hey, you better go look at this, it isn't working right.
That's certainly, the last people you want to ask, is it okay to launch, is the crew. They'll say yes no matter what's happening.
And we do ask them, by the way, but it's a formality because we know what the answer is. Unless he's got a fire extinguisher up there putting out something in the spacecraft, he's going to say, we're go. And that's also why we put in a rule. It says after 5 minutes for these critical launch commit criteria items, the 500 that you absolutely have to look at and certify, you don't proposition us with the change to that after 5 minutes because we're not going to entertain it. If they're out of limits, we're not going today or tonight. It's going to be at least 24 hours, a long time. But the team that does it, they're good. They're professionals, and and we talk a lot about the Apollo program and how great things were back then. But I just gave you the example of Apollo 13. The shuttle team versus the Apollo team has a much higher degree of difficulty situation to deal with. There's fewer people on shuttle, yet it's a more complex vehicle than the Apollo, the whole Apollo system. The Saturn V rocket and the spacecraft were simple compared to the shuttle system. And we had 25,000 people at the Cape in the Apollo program flying 2 to 3 times a year. And in the shuttle program back in the early 90s, we flew 7 times a year with 6,000 people. With a vehicle that's more complex, older. In the Apollo program, our ground equipment was new and all the flight hardware was new. It wasn't reused. It was fresh, out-of-the-box, factory, pristine stuff. And the requirements were easy. It had to act and look brand new, or you replaced it. The shuttle, because it's 20, 30 years old, depending on which orbiter, and the ground equipment, which is 30 to 40 years old, there's requirements that allow fair wear and tear, so that you have a lot. The engineers are constantly pushed with the, is this good enough? You know, these wire bundles are frayed, and there's dings in this line, and that weld is looking like it's got corrosion on it. Is it good enough? Well, they're constantly propositioned with that. Where back in the Apollo program, you didn't have to mess with that gray area stuff. It either looked or acted brand new, or you replaced it. And replacing it was easy because money was unlimited. As a journeyman engineer on Apollo, I was told, hey, whatever you need, you can have it. You know, system engineer Sieck, more test equipment, you need more technicians to be trained on this over here. Whatever you need, just ask for it. Money's not an object. As a manager on the Shuttle program, when I finally got promoted out of the job I liked, the launch director, I had to tell the journeyman engineers, hey, this is all the money you get for next year. You gotta be real efficient with this and frugal, because next year you're probably going to get less. And your strategy and approach to issues is much different if you have those two different environments to deal with. And finally, the other thing, you know, that Shuttle deals with today versus Apollo is the acceptance of risk. I mean, I already mentioned Apollo 13. Back then, if you made a mistake, you pat it on the back, say, hey, nice try. Now, is there anything, you know, can be done to better enhance your probability of success? Whereas in the Shuttle program, you know, risk aversion in this country, you know, I won't get started on that tangent, is becoming more and more our lifestyle. We don't want to do things that we might lose, you know, or we may not win, or we may not be successful. And risk is, you know, there's less tolerance to it. And when you have a problem like Columbia or Challenger, you know, you get half a dozen boarding parties coming into NASA saying, here's what you need to do different, or this is wrong with your agency, and this, and you need to go fix that. And again, back in Apollo, that's a good place to go. It was, what do you need to be successful? Much different, and it makes it difficult to operate.
Well, could you comment upon risk aversion in the launch director, and whether there are differences, whether there are more aggressive and more conservative people who've had your job?
Well, I would say before I was launch director, there was one other launch director, and he was more aggressive than I was. You know, he was the consummate ops person, and he would push until, you know, you'd say, Uncle, I surrender, whatever, and then he'd make a judgment call. I was more conservative than that. My success, I trained the one immediately after me, and he was pretty much the same, but he got, you know, the highly visible job. Management saw that, you know, hey, this guy is good. We'll take him away from here and go put him over here managing, you know, this large organization and worrying about budgets and contracts. It's the same thing that happened to me, and that's I mean, that's unfortunate, because but that's NASA's strongest suit is not succession planning. Unfortunately, it just isn't. Yes.
So are you saying now people, the Shuttle program is too risk averse? Is that what you're trying to say? Because you also said that, you know, for example, it's your job as launch director to be conservative and just say no when everyone else is saying yes.
No, I wouldn't say that the Shuttle program is risk adverse. I'd say our society is risk adverse, and you see some of that permeating into the Shuttle program, but not to the point where I would say it's, you know, it's detrimental. I mean, asking questions, you know, digging in to understand what your risks are is an important thing to do. And early in the Shuttle program, we didn't do that. We had a lot of confidence in the hardware. After the first few missions, it's just like a new car. You know, you put 5,000 miles on it, you get the bugs out of it, and you fully expect it to last another so many 100,000 miles. Well, that was the same expectation in the Shuttle program. You fly a few flights, and you learn that the tiles really stay glued to the orbiter, and the thermal control system really responds as it should on orbit in managing the temperature and the coolant loops and that sort of thing, and you build up confidence, and you say, you know, that it should work now. We got the bugs out of it, and we can go fly this thing as often as those guys at the Cape can turn it around. But what they didn't consider, and what all these engineers, with all due respect, that you heard from that certified their systems, they didn't totally capture the environment that the shuttle sees over the long period of time in their initial certification. They didn't capture it. And that environment includes not only what happens in space or the calendar exposure to just time on some of these systems that have soft goods in them, for instance, O-rings and that sort of thing, but it's the environment of the Cape with people constantly removing hardware, disconnecting things, moving wire bundles out of the way to get access to this or that other component to implement the requirements that were levied on the Cape to do the tests and inspections. And they're very invasive, and collateral damage is a way of life when you're crawling around in the orbiter. So to put in policy that tries to compensate for the fact that the certification didn't capture that environment that this hardware has seen for the last 20 to 30 years, and to reduce the unknowns involved in that's the right thing to do. You know, they're trying to reduce the risk of reflying a very complex vehicle. So that's fine, but you take that to a limit. I mean, you can talk yourself into never flying. It'd be pretty easy to go do. And in this recovery after the Columbia accident, that was starting to happen. You know, the managers, because they had this investigation board report that says, you know, NASA, you became complacent and overconfident. And by the way, in my opinion, that's somewhat of a bum rap to say that NASA in general, and particularly the shuttle program, had fallen into that mode. But to have the pendulum swing the other way to say, understand what your risks are, and then you can have knowledge on whether you decide to accept it or not. That's a good thing. But what didn't happen after Columbia, but we did do after Challenger, is after we understood the root cause of the accident and some of the other factors like communication that were part of that, reviewed all the systems, all the requirements. The managers said, look, we're willing to accept some risk. You people who are responsible for these systems and these processes at the Cape, you need to quantify that for us and bring it to us. And we'll either say, okay, we don't accept that, you go back and change your system or change your limits or do more tests or whatever, or we will accept it. You know, we'll say we'll accept that risk. Management will accept some risks. That happened after Challenger, and we were able to fly again, you know, roughly 2 years later, after we recertified the design to the solid rocket motors. That didn't happen after Columbia, and you can speculate whether or not, you know, we could have flown 6 months ago or a year ago, or we should have waited longer to fly because we still had a piece of foam come off the tank. You could debate that, but management never acknowledged that they were willing to accept some risk after Columbia. They did say, tell us what the risk is, but we really want you to crank it down to zero. We don't want to take any risk, unlike Challenger. Now, is that bad? I don't see. What really happened with Columbia was there were the mission management team, their discipline had eroded, and there was communication issues. I mean, if you're a student of that investigation, they didn't grade out very well. But the investigation said, you know, there's complacency and overconfidence in the system. Well, having been part of the system prior to my retirement 5 years ago, that you never found any complacency or overconfidence with the engineers, the technicians, or inspectors, or the managers that I knew. Now, they weren't as smart as they thought they were, or in some cases as smart as they needed to be, but that's not the same as complacency or overconfidence, because the latter, to me, implies an attitude problem, that I've got it knocked, I know it all, you know, I'm as smart as I need to be. And I never sensed, for the most part, You know, there's some people I didn't like because I thought he or she was arrogant or something like that, but I never sensed an attitude problem with the shuttle team, and you know, from the technicians, many of which I knew and grew up with, to the top managers in the shuttle program. I never sensed that. But were we not as smart as we thought we were, or as smart as we needed to be? Were there signs that, you know, there's something going on here that you ought to go fix? Yes, but again, you know, they didn't just blow off, so to speak, these problems we were having with foam on the tank and these other systems, which to me would have been, you know, that's complacency or overconfidence. Anything else?
We're just about out of time. I've got 2 announcements. I've been working with the Stellar people. As you know, some of the PDF files that I've tried to load didn't load. They can't really figure out why, but I've sent them the files. They've loaded most of them on. So hopefully almost everything is there. We're continuing to work at it, but hopefully all the things that you need access to you can find. I said there were 2 things, but that's the only one I remember.
Well, let me close with one note then. Okay. I'm glad you're here. Thanks for your choice to pursue an engineering career, doing things that are hard. I've found it in my travels that unfortunately there's fewer people deciding to pursue the tough curriculums and the occupations that require a lot of work and have some risk associated with them. But it's encouraging to see people in graduate school that want to do what I did. I'm not sure how much engineering I did in my 40-year career. I did a lot of managing and a lot of other assignments, but I'm sure you can accomplish a lot. I had a grandmother who was born at the end of the 19th century, and when she was your age, there weren't any computers, airplanes, cars, you know, TV and that sort of thing. Yet in her lifetime, she got to see her favorite grandson, Bobby, help put a man on the moon. You know, now I don't know what it can be done in your lifetime, but you can make great things happen with the career you've chosen. So thanks for choosing it, really.
Bob, thanks very much.
All right. Pleasure.